Okay, today we'll have a brief lecture on asymptotic growth of functions. A quick recap of what we have done till now about analysis of algorithms. To solve an algorithmic problem, we have to design an algorithm, construct the algorithm correctly, and finally analyze the algorithm. What do we mean or understand by analyzing the algorithm? Running the algorithm takes resources such as time and memory. Calculating those resources, especially the running time, analytically is what we mean by analyzing the algorithm. We calculate the running time of an algorithm analytically without actually executing the algorithm. We don't need to run the algorithm on a real machine in order to calculate the running time it takes for execution. That is the meaning of analytically. How long an algorithm takes for execution? The running time depends on several factors. One, the input size to the algorithm, the nature of the input, such as the input is sorted or not, and the actual machine executing the algorithm or the algorithm's operations. The real machines are too complex. We are interested only in knowing two things about an algorithm. Is the algorithm practically efficient? Secondly, how does the algorithm compare with another alternative algorithm? So comparison of algorithms is the real intention. For that intention, we don't need the tedious details of an actual machine. Therefore, to analytically calculate the running time, we consider a simplified model, abstraction of a machine. We call that random access machine, RAM. Very important observation about the RAM machine is it has an instruction set or operation set. The basic operations execute in constant amount of time. Independent of the input size. For example, to add two numbers takes a fixed amount of time. It does not depend upon the numbers. To multiply two numbers takes a constant amount of time. Whereas to calculate the factorial, the time it takes depend on the operand. So how do we analyze the algorithm? We have to identify the basic operations, the constant time operations done in the algorithm, and count the total number of times these basic operations are executed. In an iterative algorithm, the basic operation in the innermost loop body dominates. After we have counted the total number of times the basic operations are executed, we will approximate it by an order of growth or growth rate. If the algorithm has a best running time, average running time, worst case running time, then most often we are interested only in the worst case running time. Growth rate or order of growth or asymptotic growth. Till now, we have not precisely defined what we mean by asymptotic growth rate or order of growth. All we said was, suppose the running time is a function such as an squared plus bn plus c. I said ignore the lower order terms. Bn is a lower order term, C is a lower order term. And then in the highest order term, ignore the multiplicative constant or multiplicative coefficient. That leaves us with n squared. Then we say that an squared plus bn plus c is big O of n squared. Quadratic running time. We said when the value of n is small, it may not be true, but as n becomes very large, this is true. That is all we have been doing about growth rate or asymptotic growth rate till now. In this class, we will define asymptotic growth rate precisely. This is an overview. Running time of algorithms. How do they grow when the input size becomes very large, approaches infinity? We are interested in the asymptotic growth of functions. This word asymptotic simply means in the limit. When n becomes very large, we know that suppose we are given a function f of n, as n increases, f of n also increases. We know that. But we are not interested in how f of n grows when n is small. We are interested in knowing how f of n grows or increases when n becomes very large. Those are the words. Very large, in the limit, approaches infinity, and so on. So, running times of algorithms are expressed by their asymptotic growth. Not by how they grow when n is small, but only when n is large. It is very important. We are interested in how the running time function grows when n is large. We don't really care how f of n grows when n is small. Informally, we will introduce this asymptotic notation or growth notation. Compare growth of functions using big O, big omega, big theta, small o, small omega. They are roughly equivalent to big O is roughly or informally less than or equal to small o is less than, big omega is greater than or equal to, small omega is greater than, and big theta is equal to. Suppose f and g are two functions. When we write f is big O of g, note how I read that. I simply read f is big O of g. I did not read f is equal to big O of g. F is big O of g. This means f is less than or equal to g. I would like to use a notation something like this, a relation. This means f grows slower than g, or f grows as fast as g. Of course, this growing slowly or faster or as fast as, we are interested only in f is equal to big omega of g is informally f is larger than or equal to g. In symbol, we should read f grows faster than or as fast as g. When n increases, f also grows, g also grows. There is no question of f growing in value and g growing in value. The question is which grows faster or which grows more slowly. As n becomes very large, f of n will also become very large. G of n will also may become very large. That is not my interest. My interest is between f of n and g of n, which grows faster. F is equal to big theta of g means f grows as fast as g. F is equal to small o of g means f grows strictly slower than g. F is equal to small omega of g means f grows faster than g. Compare these things, big O and small o. F is equal to big O of g means f grows more slowly or as fast as g, whereas small o means it grows more slowly. Similarly, big omega and small omega. Big omega means f grows faster than or as fast as g. Small omega means f grows definitely faster than g. This is an informal notation. Now let us define. Read only what is in the box. What is asymptotic growth rate or simply asymptotic growth? As input size n increases, the running time f of n also increases. This asymptotic growth rate can be discussed for any function f of x and g of x. But we are interested only in the running time functions. Therefore, our discussion will be in the context of running times. So, as n increases, approaches infinity, f of n also increases, no doubt. Our interest is how fast f of n grows as n becomes very large, approaches infinity or in the limit. Let us define these three asymptotic notation, big O, big omega, and big theta. We are given a function f of n. Informally, when n is very large, if g of n is always greater than or equal to f of n, we say that g of n is an upper bound of f of n. Or we simply read f of n is big O of g of n. Okay. Growth of a function f of n can be described by an asymptotic upper bound. What is asymptotic? Upper bound when n is large. So whenever you see the word asymptotic, immediately you imagine, okay, we are speaking about very large values of n. Millions, billions. That we write as f of n is big O of g of n. That means g of n is an upper bound for f of n. Informally, g of n is always above f of n graphically. G of n is always greater than or equal to f of n. Only then g of n is an upper bound. But that is very loose way of saying. We have carefully put a C. It is not that g of n is always above f of n. It is enough if a constant times g of n is above f of n. Then we say g of n is an asymptotic upper bound of f of n. Note it carefully. It is not necessary g of n is above f of n. It suffices, it is enough if a constant time c times g of n is above f of n. Then we say g of n is an asymptotic upper bound of f of n. Even this need not always be true. For example, here, look here, in these areas, constant times g of n is below f of n in this area. C times g of n is below f of n in this area. So even this, that f of n is always less than or equal to c times g of n need not be true always. It is enough if it is true for large values of n. I will say that for all values of n larger than or equal to n0, if this is true for n greater than or equal to n0. That is the definition of big O, working definition. Fn is big O of g of n is equivalent to saying there exist two constants c and n0 such that f of n is less than or equal to c times g of n for all values of n larger than or equal to a n0. This n0 itself may be very large. It may be 1, 10, 100,000, anything it may be. Now I said carefully, I don't read this as is equal to, f of n is equal to big O of g of n. That is not the way I read it. I read this as f of n is big O of gn. The symbol is equal to, but I read this as is. After all, programmers are used to abuse of this notation. You use is equal to symbol for assignment, but actually it is not is equal to operator. It is an assignment operator like this. Why do we read this as f of n is big O of g of n? Here is a reason. If you consider the c times g of n, there may be a large number of functions. This is another function. This is f1 of n. This may be yet another function, f2 of n. This may be yet another function, f3 of n. G of n is an upper bound, asymptotic upper bound for f1 of n, f2 of n, f3 of n. So this big O of g of n actually does not refer to a single function. It refers to the set of all functions which are below c times g of n. Our own f of n is one among these f1, f2, f3. Therefore, instead of saying, okay, big O of g of n is not a single function, it is a set of all functions such that there exist positive constants c and n0 such that f of n is less than or equal to c times g of n for all values of n larger than or equal to n0. So, the precise notation is this. F of n is in big O of g of n. Big O of g of n is a set of functions. All functions, g of n is this. I said all functions. All the blue functions are in the set big O of g of n. F of n is one such function. F of n is in big O of g of n. That is what we mean by writing f of n is equal to big O of g of n. Let me ask a question. This is the precise notation. This is a loose, informal notation. In this case, do you think we are allowed to write big O of g of n is equal to f of n? Can you answer this question? Just now I define whenever we write f of n is big O of g of n is equivalent to, we actually mean f of n is in big O of g of n. If this is the meaning of big O, are we allowed or is it meaningful to write big O of g of n is equal to f of n? Yes or no?
No, sir.
It is not meaningful. It is something like this. After all, you write variable becomes v plus 2 in a programming language. Are you allowed to write v plus 2 is equal to v? You are not allowed. Because even though the symbol is equal to, actually it is an assignment operator. The side matters. The left side becomes right side. In a similar vein, even though the symbol is equal to, actually we mean only is in. Therefore, you cannot exchange the two sides of the equal to symbol. Very important. One such example is here. N squared is an upper bound of 2n plus 20. This does not mean the curve n squared is always above the curve 2n plus 20, but beyond a certain value. This is n0. a constant times n squared is always above 2n plus 20. That is what we mean. Big omega notation. Like big O is asymptotic upper bound. Big omega is asymptotic lower bound. So we are given a function f of n. We want to say g of n is a lower bound for f of n. G of n is always below f of n, or f of n is greater than or equal to g of n. That is what we mean by saying f of n is big omega of g of n. When we write like this, we mean g of n is a lower bound for f of n. F of n is always above g of n. But when I say this, I mean f of n is always above a constant times g of n. Informally, I will say g of n is an asymptotic lower bound. Actually, I mean f of n is less than or equal to c times g of n. As I said before, even this need not be true for all values of n. This needs to be true only beyond a certain value of n, such as n0. So the definition is very similar to what we gave before. F of n is big O of g of n is equivalent to saying there exists constant c and n0 such that f of n is always greater than or equal to c times g of n for all values of n above a certain value n0. Again, big omega of g of n is not a single function, it is a set of functions. All functions above all these blue functions are in the set big omega of g of n. Our own f of n is one among them. Therefore, big omega of g of n is a set of all functions such that f of n is greater than or equal to c times g of n for all values of n greater than or equal to n0. And therefore, whenever we write f of n is equal to big omega of g of n, this is equivalent to saying f of n is one function, is in the set big omega of g of n. Now for big theta, g of n may be an upper bound of f of n. F of n is big omega of g of n, means g of n is an upper bound. If f of n is equal to big omega of g of n, then g of n is a lower bound. Suppose we can find two constants c1 and c2 such that c2 times g of n is an upper bound for f of n and c1 times g of n is a lower bound for f of n, then we say g of n is a tight bound, asymptotic tight bound. F of n and g of n are almost equal asymptotically. Okay, that is the definition of big theta. F of n is equal to big theta of g of n is equivalent to there exists constants c1, c2, n0 such that f of n is in between c1 times g of n and c2 times g of n for all values of n larger than or equal to n0. Again, g of n is a set, and therefore whenever we say f of n is equal to big theta of g of n, we mean f of n is in the set big theta of g of n. And it is very easy to see that when g of n is a tight bound, asymptotic tight bound for f of n, both are true. F of n is big O of g of n and f of n is big omega of g of n. Or we could have also written f of n is equal to is big O of g of n and g of n is. Let me ask a question here. When we are analyzing an algorithm, okay, suppose our running time is 2n plus 20. And Cn square is above this. Suppose I write this is Cn cubed. I may have a Cn power 4. Answer this question. Is n squared an upper bound for 2n plus 20? Yes. Is n cubed an upper bound for 2n plus 20?
Yes, sir.
N power 4 an upper bound for 2n plus 20?
Yes, sir. But
Yes.
n
Yeah.
is least upper bound.
But we never discussed about least upper bound. We said 2n plus 20 is big O of n squared. I can also write 2n plus 20 is equal to big O of n cubed. I can also write 2n plus 20 is equal to big O of n power 4. So, an algorithm's running time is big O of a function. Doesn't say yes, it is the, as you said, it is the tightest upper bound. There is no such guarantee. So, what we are more interested would be big theta of something. Big theta will be a tight upper bound. Big O and big omega are not tight upper bound or tight lower bound. Very important. Okay. These asymptotic upper bound, asymptotic lower bound, asymptotic tight bound may also be expressed in terms of limits. Suppose, consider this. F of n over g of n is equal to 0 as limit as n tends to infinity. Which one grows faster, f of n or g of n? If the limit is 0. F of n is growing, g of n is also growing, but in the limit it is 0. Which one is growing faster? Only if this is something like this is 1 and this is infinity, 1 by infinity will be 0. Therefore, g of n is growing faster than f of n. Therefore, we say if limit of f of n over g of n as n tends to infinity is equal to 0, f of n is big O of g of n. And you may say g of n is not big O of f of n. All right. Equivalently, you may say f of n is big O of g of n, but you cannot say it is a tight bound. F of n is not theta of g of n. A similar argument, if limit of f of n over g of n as n tends to infinity is infinity, this is possible only if it is a something like this, 1 of 0. That is, f of n grows much faster than g of n. Then we can say g of n is big O of f of n. F of n is growing faster. Therefore, this is an upper bound. And f of n is not big O of g of n. Take time to absorb these things. Or I may say f of n is big omega of g of n. G of n is always lower. F of n grows faster, therefore g of n is a lower bound, but not tight lower bound. Interesting, most interesting case is if f of n over g of n as limit n tends to infinity is equal to a constant. This may be a fraction also, a constant in real number, let's say plus. Okay. Then f of n and g of n are asymptotically equal. F of n grows as fast as g of n. That is, f of n is big O of g of n and g of n is big O of f of n. There is only another way of saying f of n is equal to big theta of g of n. That's all. Mostly our discussion is over. Now we will work out a few examples. I will come to this later on, this limit finding thing. Okay. 3n square 100n6. 3n square minus 100n plus 6. Okay. Prove that this is big theta of n squared. These typical examples you may be asked in the test. You have to prove 3n squared minus 100n plus 6 is equal to big O of n squared. You should also prove 3n squared minus 100n plus 6 is equal to big omega of n squared. Only then you have proved that it is big theta of n squared. You have to find out two constants c and n0 such that 3n squared minus, I'm sorry, wait a minute. Okay, fortunately it's here. 3n squared minus 100n plus 6 is less than or equal to c times n squared for certain value of n0, for values of n greater than or equal to n0. What can you say about this? Can you choose a value for c? Okay, let me try. This would mean bring all these terms on the left to the right. So c minus 3 n squared plus 100n minus 6 is greater than or equal to 0. Now let me put c this value. C is equal to 3. What will I get? 100n minus 6 is equal to greater than or equal to 0. For what values of n this quantity is true? This is true. This relation is true. For all values of n larger than or equal to 1. Therefore, my constant c is 3 and n0 is 1. For constant c is equal to 3 and for all values of n larger than or equal to 1, I have proved this. Similarly, I have to prove this side. Find two constants c and n0 such that 3n squared minus 100n plus 6 is greater than or equal to a constant times n squared. I have to find c and n squared, n0, I'm sorry. Let me bring c the other side. 3 minus c n squared minus 100n plus 6 greater than or equal to 0. Okay. Now, for the time being, let me forget the 6. Then I may say 3 minus c n squared minus 100n is greater than or equal to 0. 3 minus c n minus 100 is greater than or equal to 0. Therefore, n 100 by 3 minus c. Let me put c a value 2. Then this will be n greater than or equal to 100. And therefore, what should be n0? N0 may be just 1. For all values of c is equal to 2, for the constant c is equal to 2, and for all values of n greater than or equal to Oh, sorry, not in. I'm sorry. This is wrong. Is equal to 100. I have proved that 3n squared minus 100n plus 6 is greater than or equal to cn squared. Since I have proved both, this f of n is big O of n squared and f of n is big omega of n squared, I have shown that 3n squared minus 100n plus 6 is equal to big omega of n squared. Sorry, big theta of n squared. Let me prove it in another way. 3n squared minus 100n, another proof. Plus 6 is equal to big theta of n squared. Look at the definition of asymptotic growth rates using limits. In order to show that f of n is equal to big theta of g of n, all I have to show is limit as n tends to infinity of f of n over g of n is equal to a constant. Let us try that. Limit 3 of n squared minus 100n plus 6 over n squared as n tends to infinity is equal to, as such if you apply, both will be infinity. Divide both numerator and denominator by n squared, we will get limit n tends to infinity 3 minus 100 by n plus 6 by n squared over 1. Now we can substitute n is equal to infinity, we get 3 minus 0 plus 0 by 1, which is equal to 3. This is a constant, a real number. Therefore, 3n squared minus 100n plus 6 is equal to is big theta of n squared. Personally, I find this using definition, using limits is more convenient. The first proof, I have to grope in the dark, kind of, for constant c and the lower value n0, for the threshold n0. Very often find that is more difficult and more time taking, this finding out c and n0, than using limits. Okay. Just one more thing. You can try and let me know. Prove that log n is big theta of, one more proof. You cannot find constant c and n0. So I will use the definition of limit. Limit log n to the base 2 square root of n as n tends to infinity. Log of n to the base 2 can be written as log n to the base e over log 2 to the base e, which is ln n by ln 2. Using this, I can write this as 1 by ln 2 limit as n tends to infinity ln n by, again this is hard. If you substitute infinity, log infinity, what is that? Therefore, apply, I don't know how you read that. Do you read this as L'Hopital's rule? Differentiate both numerator and denominator. So you get 1 by ln 2 limit as n tends to infinity. This should be 1 by n over minus half. Okay. This is 1 by ln 2 limit n tends to infinity. What is this? 2 times 2 by n Okay, I continue here. This is 1 by ln 2 limit as n tends to infinity 2 by square root of n. Now I know this is 1 by ln 2. Substitute infinity for square root of infinity, that would be 0. Okay. Oh, this is wrong. I should not say big O of n. Look at the definition of thing. The definition is limit f of n over g of n as n tends to infinity. If this is equal to 0, then f of n is big O of g of n. In fact, it is small o of g of n. Therefore, I can write this is okay. Log n is big O of. All right. I think this level of ability to work with asymptotic growths is enough. We have already seen these common asymptotic growth functions. You should be able to prove that log n is grows more slowly than n grows more slowly than n log n, which grows more slowly than n squared, which grows more slowly than 2 power n, which grows more slowly than n factorial. Any of these things you should be able to show. Given a set of functions, you should be able to order them in this way. And do these examples as homework. For example, in the last thing, show that 2 power n plus 1 is equal to big theta of 2 1. How will you show that? That's very simple. Let me use limit. Limit 2 power n plus 1 over 2 power n as n tends to infinity. This is equal to limit n tends to infinity 2. This is equal to 2. Therefore, 2 power n plus 1 by definition of big theta of 2 power n. Very simple. These are some of the properties of asymptotic functions. I leave it to you to go at leisure. A small example. Very interesting example. Go through that. I am done.